Hello everyone. Welcome to the fourth lecture of the fourth module, which is on flash memories. The disclaimers remain the same. And in this kind of part, we'll be reading about this multi-level capability of cells. So let us first look at this multi-layer thing that we were actually discussing in the second lecture. So in lecture 2, we kind of looked at this multi-layer thing where, we stack L layers of memory on top of each other using 3D integration techniques. And if we have L layers stacked on top of each other, effective cell size reduces by 4f square by L. So let me write that. So if L layers are stacked, cell size effectively gets reduced by how much? If one of the cells was occupying 4f square area, it gets reduced by L times. So now it becomes 4f square by L. What that implies? Your density or memory density increases by L times. Now the question that arises here is, can we have a similar increase in the density without even stacking different layers in 3D? Yes, we can have such a provision. So when will that provision be there? So if we can realize several pieces of information using a single device or a single memory cell, then what we can do is, then we can effectively increase the density. Now, let us say by how much. Now the question arises, by how much? So, if one cell can be used to represent n bits instead of 1 bit, then we can increase the density by n times. Now the thing is, if one cell has to encode n bits, so n bits contain 2 raised to power n pieces of information. So to encode n bits, your device should be able to show 2n different levels, and each level would encode 1 piece of information. So let me write that as well. So n bits encodes 2n pieces of information, and if each piece of information is represented by 1 level, you can encode n bit information with 2 power n different levels. Now what are these levels? So these levels can be threshold voltage for flash, because your data is stored in terms of threshold voltage. It can also be resistance or conductance for the case of RRAM, or your phase change memory, or conductive bridge RAM, or STT-MRAM also. And this would be polarization for ferroelectric RAMs. So if you can have one device which shows several such levels which are distinguishable, then you can encode more than 1 bit of information per memory cell. And that way you can increase the memory density further. Now, if you have to encode these 2 raised power n levels, let's talk about flash memory. So, if you have to encode 2 raised power n different levels, what that means is you need to have a precise control over your threshold voltage, right? If you want to restrict your threshold voltage to some particular level, then you need to have a precise control over the threshold voltage. What that translates into? That means that you should have precise control over the charge injected into your floating gate. How you inject charge into your floating gate? It's via CHE or your FN tunneling mechanism. So to have a precise control over threshold voltage, you need to have precise control over the charge injected into FG. So you need to have a precise control over these physical mechanisms as well. And these physical mechanisms such as CHE or FN depend upon the pulse amplitude and the pulse duration for which they are applied. So that simply translates into a precise control over the pulse duration or the pulse amplitude which you are using. Or let me just write it as well. So this simply translates into a precise control over pulse duration and amplitude, or it means that your programming process or even the erase process should be very efficient. So how people achieve this multi-level capability is, let's say we are having the threshold voltage on the x-axis. So let's say this is the threshold voltage for your erase state, and this is the threshold voltage for your program state. So people tend to quantize. So what is the memory window? This is your memory window, right? So what people do is people tend to quantize this threshold voltage range between the extreme program and extreme erase states into several different intermediate levels, and then they tune their programming pulse. So then what they do is they tune their programming pulse, programming or erase pulse, to restrict the threshold voltage of the floating gate cells within these intermediate ranges. Okay, so this is how people kind of achieve this multi-level programming capability. So what they do is they kind of tune their programming or erase pulse to restrict the threshold voltage of the device, or to restrict the charge on the charge which has been injected or extracted out of that floating gate, so that its threshold voltage lies in some sub-range. So in that case, the kind of distribution of different threshold voltages, like we had the threshold voltage distribution for when we had only 2 states, erase and program states. In multi-level, what happens is the kind of distribution, threshold voltage distribution that you see is something like this. So you have Gaussian threshold voltage distribution for each of these intermediate threshold voltages. So this is the best case scenario. There is no overlap between the Gaussian tails. So here it is kind of identifiable. Here they are identifiable. Why they are identifiable? Or why they are distinguishable? They are distinguishable because there is no overlap between the tails of Gaussian distribution of adjacent VT levels. If there is kind of overlap, let's say there is this Gaussian distribution goes like this, this Gaussian distribution goes like this. So in this region, it becomes non-deterministic. And the worst part about this is if you lose, so let me write that as well. So the worst part about MLC is if you lose even a single piece of information or a single level defect, your memory no longer remains n bit. It becomes n-1 bit. So you can only, show n-1 bits. So there is a loss of 1 bit the moment even a single piece of information goes wrong. So that is one of the major defects, I would say, in this MLC. So the first requirement for MLC is you should not have any Gaussian overlap, like you should not have overlapping Gaussian tails. And how do you ensure that? You ensure that with a proper programming scheme. Programming scheme or mechanism. What is the second requirement? So the second requirement goes in the read. So how do you read this kind of a multi-layer capability or multi-level capability cell? So you kind of compare parallelly. So you parallelly compare the VTH read or the current read with several references. So if the number of bits is small, let's say it's 3 or 4, it's still manageable. But if the number of bits or if MLC exceeds 4 bit, then your read circuit becomes really complex and not feasible actually. So then what people go for is, they go for sequential reading or sequential comparison. Okay, so that is a constraint on the read. Now what else? You also want that your memory window here should be as large as possible, right? So as to accommodate different states which are non-overlapping. So you also want your memory window to be as large as possible so that one can accommodate several such levels which are non-overlapping. So what is this extreme state, or what this extreme state corresponds to? So this extreme state corresponds to maximum number of electrons which floating gate may hold. And this corresponds to 0 electrons. So in between this, or the threshold voltage difference between this case when you have maximum number of electrons in your floating gate and when you have no electrons in your floating gate, that should be as high as possible to facilitate this multi-level capability. Now we saw that an important requirement for MLC is that your distribution of this threshold voltage distribution of these intermediate levels should be as narrow as possible, right? So there should not be any overlapping Gaussian tails. If you remember from your previous lecture, your CHE is relatively immune to your process variation, or it gives you a narrow VTH distribution, right? As compared to, or as compared from your FN. So CHE is kind of a blessing in disguise, although people consider this as a negative thing for logic because it kind of degrades your MOSFET's performance, but in memories, just because it gives you a kind of very narrow distribution, it is kind of a blessing. And also, one more thing is there. And what is that? So, under proper biasing conditions, what happens is the relationship between your threshold voltage to which you have programmed your device to, so your programmed threshold voltage, and the gate voltage that you apply during your CHE is linear. So this kind of makes the life of memory engineers really easy. On top of it, the best part is that this slope or this relationship is not only linear, but also the slope is unity. As you can see here, the number of pulse or the gate voltages that you have applied during your CHE. So in CHE also you need gate voltages, right? So you must be thinking, why do we need a gate voltage in CHE? So in CHE, your gate voltage kind of provides a transverse electric field, right? And it attracts electrons towards, or hot electrons, let me write, attracts hot electrons which are flowing in the channel towards your floating gate, right? So that is the role of this gate voltage. It kind of, we told also in the previous lecture that it kind of facilitates the program process. So what people do is they kind of apply the same drain potential, but just by changing the amplitude of your gate voltage, the control gate voltage basically, VCG, let me see, write that as VCG. Just by changing the amplitude of VCG, they change the VT. And since the slope is unity, I mean, you can see over here, VGP or the control gate pulse or the control gate pulse amplitude is shown on your x-axis on top, and the change in the threshold voltage is kind of shown on your y-axis. So you can see that as your amplitude of the gate control gate voltage changes, it changes your threshold voltage as well, and the change in the threshold voltage is kind of same as, almost same as the change in what? The change in your applied control gate voltage. So this is kind of a blessing in disguise. Just because of this, you can precisely tune your VTs into those intermediate levels. So many people were asking me this question on WhatsApp that CHE is bad. CHE leads to a lot of energy consumption because it leads to a large current flow, right? Large current. But still, why do people use it for norm? Or why is it even used then? Only reason is, since you have a narrow VT distribution, and since you can program the cell, you can kind of program the cell precisely to intermediate values, thanks to this kind of a linear slope between BGP or the control gate potential and the change in threshold voltage. Because of these reasons, CHE is a gift. to memory designers. Okay. Now the question arises, since Fn shows you a very broad kind of threshold voltage distribution, can we kind of use Fn for multi-level capability? So the thing is, yes, we can do it. So the thing is, even Fn can show MLC. How? There we need to come up with very, I would say, innovative algorithms. Algorithms such as ECC or program verify. So program verify scheme is an algorithm which can be used to, narrow the distribution of any mechanism. It can be used to narrow the distribution, narrow the BT distribution for CHE, for FN, of any kind of physical mechanism. Let us now look at this program verify mechanism. So this program verify mechanism, why is it used? So it is used to obtain a narrow BT distribution regardless of physical mechanism. This is essentially a programming algorithm, okay, which can give you a very tight distribution, tight BT distribution. So how it works? So let me show the sequence of pulses that you apply in your program verify technique. So as the name suggests, let's say this is the time. So it kind of tells you, and this is, let's say, amplitude of the pulse, programming pulse that you are applying, or amplitude of the pulse you are applying, not necessarily programming pulse. So what happens here is, let's say you have to, program yourself. So you kind of applied a positive potential on the gate to extract some charges onto your floating gate. Okay. Immediately after this, what you do is you apply verify pulse. So let me write somewhere that this is your program pulse, which is changing the VT state, and the ones shown in red are verify, or also known as read pulse, which just tell you the state without changing it. So your verify pulse is very small. It's close to your read pulse. It doesn't change this memory state. It doesn't change your threshold voltage. It doesn't inject any charge into your floating gate. It doesn't lead to any change in the resistance value in case of R ramps, the polarization value in case of FE ramps, and all those things. So it's only the program pulse which kind of changes your levels or states. Verify pulse or read pulse is just to read the state without disturbing it. So this is also called, verify pulse is also called non-disturbing read pulse. So it's very small in magnitude. So what is its benefit? So if you are applying series of programming and verify pulses, let's say you rate the pulse and then you again applied some program pulse, then what you did was you again read it, then you again applied this programming pulse, then you again read it. So what this verify pulse helps you to achieve is, so this verify pulse after each program step helps you to identify if we have reached the desired state. If we have reached, it's fine. If we haven't reached, then you continue applying programming pulses of higher magnitude. Let's say we kind of overshooted the value that we wanted to reach. We kind of overprogrammed it. We injected more number of electrons than what was needed. So then what we'll do is, we need to kind of remove those electrons. So after this, let's say we verified the state, we found that we have overshooted the number of electrons, and then we have to extract some electrons out of it. So what we'll do in that case, then we'll erase. So then we'll apply a pulse to erase it. And then we'll again verify if we have reached the particular desired value or not. So just by having a sequence of this program verify kind, or erase verify, program verify, erase verify kind of technique. So verify after each pulse, which is kind of, changing the VT states. So here, let me also write that this program can also be an erase pulse. It can also be program or erase pulse. So you apply a verify pulse after each pulse through which you want to change the state of the memory. By that, you not only achieve a narrow VT distribution, but you also achieve the desired value very precisely. That okay, I want to tune my memory to this state, and just by having a cycle of this program verify pulses, you can reach that particular desired state very precisely. So it kind of improves the precision of programming or erasing. This is particularly very useful for 3D NAND flash, which show MLC, and their MLC is now called QLC, which is quaternary or four levels, not 4 levels, quaternary or 4 bits per cell. There is another term called TLC, which is 3 bits per cell. MLC, in general, people use it for 2 bit per cell. And SLC is single layer capability, 1 bit per cell. So if you see in some memory specs that you have QLC or TLC, you simply understand that QLC simply means that each of those cells, each of those memory cells can kind of store 4 bits. If it is TLC, each of those memory cells can store 3 bits, and so on. Now let us talk also about throughput, programming throughput. So if MLC were not there, suppose you want to store 3 bits with a memory that is showing SLC, single level capability. So if MLC is not there, for representing 3 bits, you would require 3 memory cells, and then you would require 3 programming pulses to achieve or to write this 3-bit word. Now if you have some TLC memory cell, you can actually write using only 1 pulse, theoretically. So theoretically, if you see, you need 3 memory elements and you need 3 programming pulses to write a 3-bit word. However, with TLC, only with 1 pulse, you can write it theoretically. But since you want to have a lot of precision for achieving TLC, you'll do it with several program verify pulses. So it may appear, or at first hand, it may appear that your programming throughput has improved. By programming throughput, I mean number of write pulses required to program a particular bit word. Let's say in this case 3-bit word. But since you achieve this kind of level using several program verify pulses, your programming throughput remains almost same. So your programming throughput doesn't change much. Only advantage that you get is in terms of density. So now what can be the other issue with MLC? Since you are kind of quantizing the entire threshold voltage into several small intermediate kind of sub-ranges, so effectively for each of these level, the kind of window that they have or the kind of range that they have is very narrow. So if it were a only single level capability, you'll have this entire whole memory window for this 2 states. But since you have now quantized it into several small ranges, each of those levels can operate within that small range itself. So the effective memory window for those small ranges is very small. So retention is kind of a big problem. So let me write it as well. So retention is a problem in MLC. Why so? Because now your effective overall memory window is divided into several small windows. And what happens in these small windows? There are intermediate levels. Intermediate levels in these small ranges or sub-memory window. In your SLC, you have a large memory window to play with. Even if your floating gate leaks some amount of charges, since your memory window is large, you won't land up to the other memory state. But in MLC, if even small amount of charge leaks, we will land into the neighboring intermediate level. And the moment even one level is kind of corrupted, your entire n-bit thing becomes n-1 bit. So that is a big problem with MLC. So what this simply implies is the kind of charge leakage that we can tolerate in MLC is quite small as compared from your SLC. So this is the same case as was with SRAM and all. Your noise margin, noise or error margin is small. Okay. However, to add to our kind of however, if all intermediate cells or if all intermediate VTs show a similar trend, what that means is, if you look at here, this curve, all intermediate levels, let's say this is one intermediate level, this is second, this is third, this is fourth. So this is MLC, that is 2-bit information, like 2-bit information can be encoded, and there are 4 different levels. So after baking, so why do we bake? So we bake to, mimic the impact of aging. So let me just write, we bake to high temperatures to mimic the impact of aging. right? So if after baking process, or if with aging, which we are kind of observing after the baking process, if after aging all VT shift, intermediate level VTs shift in the same direction, then also distance between levels kind of remains same, and the most important part, there is no overlap. However, even in this case, we will have to tune the reference voltage for reading to obtain correct data value. So your peripheral circuitry has to be tunable in case of MLC. And this MLC works very fine with 3D NAND flash or even NAND flash just because they have something which is called ECC. I have been repeating it time and again. If there were no ECC, there won't have been any MLC, any NAND flash, any memory in general apart from SRAM or DRAM. It's just because of ECC that these have been surviving and you have been able to increase the memory density so far. So with that, the module on flash comes to an end.